Okay, so now we're going to talk about the math side of titrations and interpreting titrations. We've talked about what they are, what their function is, how we use them, but now let's go ahead and jump into that. So we have a practice problem here where we are titrating hydrochloric acid with aqueous ammonia. Or actually we're titrating aqueous ammonia with hydrochloric acid. And we're given the Kb of ammonia, and we're asked to find the molarity of the ammonia, the pH of the solution at the equivalence point, to draw the titration curve, and then talk about what species are present and choose the correct indicator. So let's go ahead and jump into the first part of the problem. So the first question is, what's the molarity of the ammonia? And so this is really just a stoichiometry problem. We're going to first write our balanced chemical equation, so we know that we have hydrochloric acid. So we have the hydrochloric acid reacting with the ammonia to form ammonium chloride. So there's our balanced chemical equation, so we can see that these are 1 to 1. So we can first start with the volume of the hydrochloric acid, which is 29.28 milliliters of hydrochloric acid. We know that for every 1 liter of hydrochloric acid, we have 0.10322 moles of hydrochloric acid. And we also know that for every 1 mole of hydrochloric acid, there is 1 mole of ammonia. And so this is going to allow us to find the moles, or as I have it set up, millimoles of ammonia. So we have 29.28 times 1.032, and we get that we have 0.1032, we have 3.022 millimoles of NH3. Now, in order to find molarity, we're going to divide number of moles by volume. So we're going to take that 3.022 millimoles of ammonia, and we're going to divide it by 25 milliliters. And we're going to get that the molarity of the ammonia is 0.1209 molar ammonia. So this is just a stoichiometry problem. You guys have done titration stoichiometry problems before. Now we're being asked to find the pH of the solution. Well, we're at the equivalence point, so that means that we've added equal quantities of hydrochloric acid and ammonia. So the pH is really now being determined by this ammonium chloride. And we're going to recognize that that ammonium ion is an acidic ion. So we're going to write our equilibrium expression for the ammonia acting like an acid. And we're going to have that we now have ammonia in solution and hydronium ions. And so we need to find the concentration of the hydronium ions in order to find the pH. So in order to find the concentration of the hydronium ions, we're going to need to do a Ka calculation, just as we've been doing to find concentrations of hydronium ions and hydroxide ions. So I'm going to write my Ka expression. Ka is equal to the ammonia concentration times the hydronium ion concentration divided by the ammonium concentration. And so we know that this starts out, well, we actually need to figure out where this starts out. We know these start out at 0. Okay, now what's the concentration of the ammonium? Well, we know that we had 3.022 millimoles of ammonia, and we know that for every 1 mole of ammonia, 3.0 millimoles of ammonia, and for every 1 mole of ammonia that we started with, we wind up with 1 mole of ammonium chloride, or 1 mole of ammonium ions. And we know that then that we have 3.022 millimoles of ammonium. And we know that we have a total volume after the reaction is complete, 3.022 millimoles of ammonium. After our reaction is complete, our total volume is 29.28 milliliters plus 25.0 milliliters. And so we're going to divide the moles by the volume to find the molarity. And we get that the molarity of the ammonium ion is 5.57 times 10 to the negative second molar. So this is our starting molarity, 5.57 times 10 to the negative second. We know that this is going to go down. These are both going to go up. And so this is going to be approximately 5.57 times 10 to the negative second, and these are going to be x. Now we have one more piece of information that we need. We need the Ka value. We're not given the Ka value. We're given the Kb of ammonia. But we know that the Ka and Kb of conjugates are related in that their product is the Kw. And so we need to solve for Ka. Kb is 1.8 times 10 to the negative fifth, and Kw is 1.0 times 10 to the negative 14th. And so from that we can learn that Kb is equal to 5.56 times 10 to the negative 10th. So now we have a Kb value, and we can come back down here. Sorry, our Ka. We have a Ka value. We can come back down here to our Ka expression. And we know that this is x, and this is x, and this is 5.57 times 10 to the negative second. So we can set up our equation, 5.56 times 10 to the negative 10th, x, 5.56 times 10 to the negative 10th is equal to x squared over 5.57 times 10 to the negative second. Confused myself with the similar numbers there for a minute. And so we're going to multiply this by 5.57 times 10 to the negative second. And then we're going to take the square root. Okay, and we get that x is equal to 5.56 times 10 to the negative sixth, and we know that that is the hydronium ion concentration. And so in order to find pH, we know that pH is equal to the negative log of the hydronium ion concentration. And so that's going to equal negative log of 5.56 times 10 to the negative 6. And we get that that's 5.255. I made a mistake on our sig figs earlier. This should only have 3 because the 25.0 there. Okay, so we now have the answer to the molarity of the ammonia, 0.121. We know the pH of the solution, 5.255. We need to sketch our titration curve. We're going to label that titration curve with what species are present, and we're going to select the correct indicator for our system. So let's go ahead and flip this over and draw a titration curve. So we have our X and our Y axis. We are titrating a strong acid with a weak base. So we're going to start out, this is pH on the y-axis, and this is volume on the x-axis. And this is the volume of sodium hydroxide. Okay, so we know that it's going to start out really low because this is a strong acid. And we also know that our equivalence point is going to come at 29.28 milliliters. So I'm going to mark this as 30, 20, 10. Here's a pH of 7. Whoops. Didn't do a very good job of making those even. Let's try that again. One last try. Alright, so here's our pH of 7. And so we know, because we are titrating a strong acid with a weak base, that we're going to have a relatively shallow curve here. And as we approach the equivalence point, which was 29.28, which is right there, this is going to dramatically shift upward. And so we're going to draw our curve so that we can see that dramatic shift upward. And then once we get past 7, we're going to come back this way. Okay, so this is what our titration curve is going to look like. We can see that our equivalence point is right about here, and hopefully that gives us a pH below 6, about 5.55. Okay, so this is our equivalence point. At this point, we have our predominant species in solution are the ammonium ion and the chloride ion. Here in this section of the graph, our predominant species are ammonia, chloride ion, and ammonium ion. Here at the beginning, our predominant species are hydrogen ion and chloride ion. And then past the equivalence point, our predominant species is NH4 plus and chloride ion, NH 3 chloride ion, hydroxide ion, and NH. Okay, so that's our species. That's our titration curve. And now we just need to choose the correct indicator. And so since this changes at about 5.5, our best indicator is going to be methyl red because it has a color change at between 5 and 6. Alright, that's it for titrations. Let me know if you have any questions.